Well, greetings. My name is James Grice, and I am Professor of Psychology at Oklahoma State University. And in this brief video, I would like to introduce you to the work we've been doing with observation-oriented modeling, which is a novel way to both conceptualize and analyze data in the social sciences. Now, I'm actually going to begin with a series of questions, and then we'll go from there. For the first question then, would you like to analyze data in such a way that you can truly focus on the individuals in your study rather than upon aggregate statistics? Now, as a second related question, would you like to avoid the p-value, or what's known as null hypothesis significance testing, which has truly been the bane of so many of our modern sciences? Thirdly, would you like to confront head-on the measurement problem in the social sciences, particularly as we have seen it in psychology? And lastly, would you like to develop causal models that are designed for the social sciences rather than for the physical sciences? Well, if you've answered yes to any of these questions, or if you find these questions intriguing, then you may in fact be interested in what we're doing with observation-oriented modeling here at Oklahoma State. Now, we chose the words observation-oriented because data analyses in this new approach are centered around graphical procedures that allow you to examine your raw data for meaningful and robust patterns. For example, we can consider these 100 contrived cases, which we have divided into two groups. We have an experimental group and a control group. Now, the outcome variable here is a quiz score that can range from 0 to 20, and we're not going to worry about the details of this study, as my point here is to demonstrate how we might analyze these data. With a traditional statistical analysis, we could begin with the computation of means and standard deviations, and then proceed to a t-test and significance test, accompanied by a bar plot of the means and standard errors. Now, by comparison, these same data can be analyzed in OOM with a Bayesian-like classifier, coupled with a simple graphical procedure known as a multigram. Now, as you can see, the distributions for the control and experimental groups are presented side by side, and the green bars represent persons who are classified correctly by the algorithm, and the red bars represent persons who are classified incorrectly. So in a single graph, we can see all of the data, and we can see the clear pattern that distinguishes between the two groups. Most of the persons in the control group scored between 9 and 14, whereas most of the persons in the experimental group scored lower or higher than these values. And overall, a whopping 84 of the 100 individuals, or 84%, were classified correctly. And this is an impressive result, and it was completely missed by the traditional statistics on the left. So we have a variety of such straightforward and compelling graphical procedures in the OOM software, and they will play important roles in how you go about analyzing your data and interpreting your results. Now, an immediate pragmatic advantage to this visual observation-oriented approach is that we do not have to worry about outliers. So in OOM, you will never have to sacrifice one of your participants to an unwieldy mean, variance, or covariance, nor will you have to worry about unrealistic distributional assumptions, such as a perfect normal curve, nor will you need to transform your data into some arbitrary metric to meet some statistical or distributional assumption. To see these ideas in action, let's consider this recent paper, in which the authors use an ingenious mechanical flower, as you can see on the right side of the screen here, to study learning in honeybees. Now in Table 1, we see the intervals between 12 visits to the mechanical flower, here recorded in seconds, for 10 honeybees in this study. Now, based on the study design and simple principles of learning, the authors expected decreases in the intervals for the first 6 trials. The intervals were then expected to increase over the last 6 trials, and these last trials were expected to be greater in value than the first 6 trials. Clearly, there are a number of outliers in the data set, and the variances within the bees are obviously quite different, as are the variances within the trials. Now, analyzing this data with traditional parametric statistics would prove incredibly challenging because important statistical assumptions are going to be violated. We also see that the 7th honeybee has missing data, which would have to be imputed before any type of analysis, or we would have to delete this honeybee from the analysis altogether. Now, by comparison, analysis of these data in the OOM software is a breeze. We simply take this ordinal hypothesis, we convert it into a visual pattern, and then we examine how well each honeybee's interval times fit the pattern. So let's now switch over to the software and see how the analysis is conducted. So here we see the 10 Bs and the 12 trials. The analysis we wish to conduct is under Analyses, Ordinal Analysis, and Concatenate Orderings. We can go ahead and move the 12 trials over, like so, and then we can define the pattern. So we'll define the pattern as we saw just a moment ago. So that's the expected ordinal pattern then that should match every honeybee's times. Let's go ahead and take a look at a couple of honeybees while we're here to see what's going on. We'll look at honeybee number 6. And the ones here indicate the ordinal relationships between her particular times. And notice from trials 7 to 10, they match up nicely. She's increasing each time from trial 7 to 10, but then we get this unexpected decrease from 10 to 11. But then we get another increase from 11 to 12. But overall, a fairly good match between the expected ordinal pattern and the observed ordinal pattern for this particular bee. Notice we get some matches, here's a mismatch, and then we get decreases in that matches, then we get an increase, which is a mismatch, but then another decrease. So we get some matches and mismatches here, but overall a fairly good match between this honeybee's ordinal pattern and the expected ordinal pattern. Now we can quantify that, and we'll see that number in just a moment. But let's first take a look at a couple other honeybees while we're here. Notice honeybee number 5, her ordinal pattern does not match expectation very well at all. Honeybee number 7 with the missing observations, you can see those are not plotted in the graph here. We get a nice match here between her ordinal pattern and the expected ordinal pattern between trials 7 through 9. And then we get again some matches and mismatches from trials 1 through 6. But again, overall, a fair amount of correspondence between the expected and observed ordinal pattern for this particular honeybee. So let's take a look at the individual results. We'll select OK here. We'll request the individual results here and select OK to run the analysis. And so we can see the individual results here clearly show that the inter-interval times for 6 of the bees fit the pattern with at least 70% accuracy, as indicated by these percent correct classification values. Indeed, all of the bees, save one, demonstrated some evidence for learning. You can see here the PCC value for the 5th honeybee was below 50%, which is not surprising given what we just saw a few moments ago. So in observation-oriented modeling, we'd like to know who is this honeybee and why did she fail to demonstrate any evidence for learning. Now the authors of the study could not identify anything unusual about this bee, but it's important to point out that with traditional statistics, she would have simply been swept into some aggregate, and anything we could have learned about her behavior or about the potential weaknesses of our study, design, or the methods would have been completely lost. So observation-oriented modeling is therefore completely consistent with what are known as person-centered or individual-centered approaches in the medical and social sciences. But focusing on individuals and staying as close to the observations as possible also proves handy for confronting the measurement issue. For instance, let's now consider this study of intra-individual dynamics. Well, using a 0 to 10 scale, students were asked to rate their daily levels of stress for approximately 50 consecutive days. They also rated daily feelings using the same 0 to 10 scale. Now the central question was whether or not different feelings might trigger stress for different individuals. For one person, for example, feeling helpless may be the trigger for stress, whereas for another person, feeling irritated may be the trigger for stress. These daily ratings could of course be analyzed with hierarchical linear modeling using the 2 levels of equation shown here and relying on the list of 5 assumptions. Notice the last assumption involves measurement, but it's important to point out here that there's no scientific evidence that stress or feelings are structured as continuous quantities. Indeed, there's no evidence that the attributes that psychometricians and psychologists aspire to measure, such as abilities, attitudes, and personality traits, are quantitative. Now to make this a little more concrete, let's suppose that John rated his stress as 10 one day and 5 the next. Was he twice as stressed the first day? Well, of course not, and the reason being that we do not have an established unit of measure here to make such a determination. Now another way to think of it, do the values 0, 1, 2, all the way up to 10 represent equidistant units of stress as you might find on a ruler? Well, again, of course not, because we do not have an established unit of measure for stress, nor do we have established units of measure for the different feelings. So with all of this in mind, what's the best way to analyze these data? Well, with observation-oriented modeling, we analyze the data at the level of the person here, but we only assume that the numbers represent some subjective awareness of more or less stress each day. So here you see the results from what's known as an efficient cause analysis in the OOM software. Now these are contrived data, and we'll look at some real data in just a moment. But here notice we have 53 days of stress ratings, and those ratings are represented by the blue line. And then we have 53 matching days of fear ratings, and those ratings are represented by the red line. Notice the 0 to 10 scale as well. Now what's important here is that the two lines match in terms of their patterns across the 53 days. For instance, if we look at days 1 and 2, we notice that both the stress and the fear ratings decrease. Then from day 2 to day 3, both ratings increase. And then from day 3 to day 4, both ratings decrease again and increase, and so on. So the patterns match nicely across all 53 days. Now if we were to quantify all possible pairwise matches across the 53 days, that would give us this PCC index, this percent correct classification index. And here for these contrived data, it's 96%. So what we see with our eye is backed up by this high PCC value. Now here are ratings from a participant in the study, and again the blue line represents the stress ratings, and in this case the red line represents ratings for feeling anxious. And again notice that the lines follow each other fairly closely across the 53 days. Now here the PCC index is 70%, not as high as 96%, but still indicating a fair degree of correspondence between the two lines across the 53 days. Now by comparison, here are ratings for feeling uncertain, and notice how the two lines do not match each other very well across the 53 days, and so the PCC index here is even lower at 44%. So if we had to choose between these two feelings, obviously the feeling anxious will be the better candidate for being a trigger for stress for this particular individual. And importantly, we've arrived at this individual-centered conclusion without having to assume continuous quantitative measurement. And finally, we refer to this approach as observation-oriented modeling, now with emphasis on the word modeling, because the most important thing you can do with the software is analyze data to compare competing integrated models. An integrated model, like the one shown on the screen here, is an iconic picture of the structures and processes believed to underlie the observations made in your study. Now, these models are necessarily more sophisticated than the simple variable-based models that you're most likely used to, but that's because we're dealing with the complexities of human nature here. And unfortunately, I cannot discuss all the nuances of integrated modeling in this short introductory video. But do notice that the models are based on participants rather than upon variables. And in this particular model, the participant's interaction with the experimenter is also included. The callout represents what is inferred to be occurring in the subjective awareness of the participant based on the researcher's explicit theory. Now, different symbols represent different aspects of that experience. Here, pentagons represent complex judgments, circles represent simple predication, and diamonds represent emotions. And lastly, different types of causes are represented in the model, including efficient and final causes. And recall that final cause for persons represents purpose, or goals if you will, and thus integrated models are distinctly human in character. Their full potential, however, becomes most apparent when competing models are pitted against one another as explanations of the same set of observations. These two models, for example, represent two theoretical explanations for data from a memory recall study. Now, results from the OOM analyses showed that the second model provided a more accurate account of the responses for a majority of the individuals in the study compared to the first model. For these participants in this particular study, then, the second model is judged as offering the best explanatory inference of the observations or of the data. Now, naturally in science, this result must be replicated, and the generalizability of the winning model must be determined through further study. But as we saw with previous examples, we arrived at this point by focusing on individuals and accuracy rather than upon p-values. So coming full circle, if you wish to focus on persons, avoid the p-value, confront the measurement problem, and build causal models for the social sciences, then please give observation-oriented modeling serious consideration. Now you can find more information about OOM in the 2011 book or on the website that you see posted on the screen here. There are a number of papers published on the website, and the software can be downloaded for free.